This is your Semester 1 review for Standard Chemistry. Please take note of your testing date. First unit that we covered way back at the beginning of the year was Unit 1, which was about lab safety and an introduction to chemistry. So this question gives us a little scenario. We have some students who are trying to figure out how the amount of sodium will affect the amount of energy given off during a reaction between sodium and water. So they're taking sodium, dropping it into some water, and measuring the energy that's given off. They use different amounts, so they measure out 1 gram, 2 grams, 3 grams, 4 grams of the sodium metal. And then they have 4 beakers with 500 milliliters of water in each, and they record the amount of energy given off. So first question is asking us about what is the independent variable. So the independent variable is what changes from trial to trial. It's what you are testing the effect of. So a clever way to remember it is that it's what I vary. IV stands for independent variable. So in this case, we can just look at our table of elements and we see what is changing for each trial. So I have 4 trials here, and each one has a different amount of sodium. So in this case, my independent variable is the mass of sodium. We are taking for each trial, I'm changing the amount of sodium, adding it to the same amount of water, and then measuring energy released. Next asks us about the dependent variable. So the dependent variable is what I am measuring. It's what is being affected in the experiment. It responds to a change in the independent variable. So I'm trying to see how this changes as I change the independent variable. It responds to the independent variable. So in this case, we see that for each mass of sodium, I'm measuring, recording a different amount of energy being released. So we see that for each different amount of sodium that there is a different energy released. What is a constant? So constants in the experiment are things that are intentionally kept the same. The researcher, the person doing the experiment, they want to be certain that the only reason the dependent variable, the energy released, the only reason that changed is because I changed the independent variable, or the mass of sodium. So in order to do that, I have to isolate these variables, so that they're the only 2 things that are going to be different. So everything else I need to keep the same. So the most obvious constant here is the amount of water. We see that for all 4 trials, the amount of water is kept constant at 500 milliliters. But there are many constants. Again, we want everything to be constant except independent dependent variables. So down to the smallest detail. I want to use the same scale, the same beakers, the instrument that I'm using to measure energy output, all of these things, the same jar of sodium, everything needs to be kept the same. What are some questions they are trying to answer? So the goal of any science experiment is to figure out how the independent and dependent variables are related to one another. So any question that puts together the independent and dependent variables is going to work. So the first question that I have, how does the mass of sodium in a chemical reaction with water change the amount of energy released? And then I have, how does the amount of sodium change the amount of energy given off? So in yellow, I have my independent variable, and in green, I have my dependent variable. So both questions just have to include the independent and dependent variables. What do you use to measure out sodium? So sodium is a metal, which is a solid, so I need to use a scale or balance to measure out a solid. So here's a balance, that's what you would probably typically see in a high school chemistry classroom. We usually stick to the electronic scales because they're a little bit easier to use. What did the students use to measure out the water? Water is a liquid, therefore we use a graduated cylinder. We do not use a beaker. A beaker has lines on the side of it that indicate the volume, but it is approximate. It is not nearly as exact as a graduated cylinder. So you could take a graduated cylinder and measure out 100 milliliters and dump it into a beaker, and it will not read 100 milliliters, I promise. Which reactant contains only one type of atom? So in this reaction, I took sodium, dumped it into some water. Sodium is, of course, Na, and water is H2O. So we see that for sodium, I've got one element, which means that I only have one type of atom. For H2O, I've got two elements, hydrogen and oxygen, so that's two types of atoms. Next unit was Unit 2, which was atomic structure and electrons. So first question, we have this table here depicting the subatomic particles. Again, sub means below, so subatomic particles are things that are smaller than an atom. They are subatomic, below atoms. So a proton has a charge of +1. Protons are positive. Neutrons are neutral, which is charge 0. And electrons are negative. Both protons and neutrons are found in the nucleus. Those two particles together make up the nucleus, and electrons orbit the nucleus. Both protons and neutrons are heavy. So remember, the nucleus is something big, it's dense, it's heavy, it's made of protons and neutrons. The mass number is the sum of protons and neutrons. Mass, heavy, so protons and neutrons are going to be heavy. Electrons are very, very light. So if protons and neutrons were an elephant, then an electron would be like a marble. That's the difference. They are so light and small that they don't even behave like particles. They actually behave like waves as well. Which of the subatomic particles is responsible for chemical properties of an atom? So again, subatomic, smaller than an atom. So chemical properties are referring to how an atom reacts with other atoms, which is bonding. Now, whenever we worry about bonding, we're always looking at the electrons. So therefore, electrons, which is how many of them, the energy level, these are what determine the properties of an atom. This table is about the different atoms. So we're looking at isotopes here, number of protons, neutrons, and electrons, and how we determine these things given different information. So first thing I want to tell you is that the atomic number is equal to the number of protons. If I take the neutrons plus the protons, that will give me mass number. Electrons and protons are usually equal unless we have a charged atom, which we will see with the first example. This bottom number here, okay, that is my atomic number. The top number is my mass number. So for the first one, for A, the number on bottom is my atomic number, which is of course my number of protons. The mass number up at top is 23. So I need to figure out neutrons. I know that if I add protons and neutrons, I should get 23. So I got to figure out what can I add to 11 that would give me 23. So that number is, of course, 12. 12 plus 11 make 23. Now I need to figure out the number of electrons. Usually protons and electrons are equal unless we have a charged atom. So here we have +1. So what this is saying is that my charges are not equal. I have a +1 charge. That means that I must have more protons than electrons. And the difference here is +1, so that's one more proton than electron. So if I got 11 protons, I must have 10 electrons. All right, next one, we start with the atomic number, which again is equal to the number of protons. The mass number is protons plus neutrons, so that's going to be 20 plus 21, which gives me 41. So now we need to write our symbol. Atomic number 20, that's going to be calcium. The number on bottom is the atomic number. The number on top is the mass number. and I've got 20 protons and 20 electrons, so the charge here must be 0. So for the next one, we can start with the number of protons. So again, the atomic number is equal to the number of protons. So if I have 20 protons, my atomic number must be 20. My mass number is 40. My protons is 20. I know that protons plus neutrons should equal 40. So if I have 20 protons, I need 20 neutrons to give me a the total mass number of 40. So once again, the atomic number is 20, so this is still calcium. But there's a difference here, and we see that our mass number is different than what it was before. So now I'm going to write 40 up top. And once again, protons and electrons are equal, so my charge is 0. All right, last one. Atomic number is again equal to number of protons, so this is 11. Mass number is protons plus neutrons, so I got 11 plus 12 gives me 23. So once again, atomic number 11 is sodium. Mass number goes on top, atomic number goes on bottom. The difference between D and A, the difference here is that for D, I see that I have 11 protons and 11 electrons. So that means my charge is 0. Alright, so what is an isotope? An isotope is going to be anything that has the same number of protons. So that's the same thing as saying that they have the same atomic number, but different number of neutrons. So we can expect different mass numbers. So if we look at calcium, we see that in this example, they're both atomic number 20, which they should be because they're both calcium. So if it was something other than 20, I wouldn't be dealing with calcium. So we have the same atom, the same atomic number, the same number of protons. The other criteria for an isotope is that we have different number of neutrons. So up at the top, we see that our mass numbers are different, which is again the sum of protons and neutrons. So we see that our number of neutrons is different. So my isotopes in this example are going to be B and C. Other question asks us which has more electrons. So we know that more electrons means that we're going to be more negative. So in this case, the most negative one is going to be sodium -1. So that one must have the most electrons. Next one is about Rutherford's experiment. So Rutherford took a piece of gold foil and he directed some alpha particles at it. So this represents my gold foil. These right here are gold atoms, and there are my alpha particles. So what he found is that most of the time the alpha particles would just go straight through. But every once in a while, one of these alpha particles would encounter something that was very dense and very positive. And this would cause them to deflect. So every once in a while, an alpha particle would hit this dense center here, and it would bounce back. And he's got a little detector, a little screen that glows every time it is hit by an alpha particle. So some of the alpha particles were deflected when they hit something very dense in the atom, which was later found to be the nucleus. So this is how he figured out that there were nucleuses in atoms. Describe what happens when an electron absorbs and re-emits energy. So in an atom, there are quantized energy levels. So there's distinct energy levels that electrons travel in. So here I have an atom with 3 energy levels, and there is 1 electron in the first energy level. So whenever this electron absorbs energy, so there's some energy coming in, it's going to strike the electron, and that causes that electron to disappear and then to reappear in a higher energy level. So this electron jumped up in energy level whenever it absorbed energy. The only way it can get back down, which is what it wants to do because that's much more stable, the only way it can jump down in energy level is by giving off this energy. So the atom, the electron, will give off that energy in the form of light. This guy will disappear from that energy level and reappear back down in the lower energy level. So light is given off as the electron jumps down in energy level, and that's what happens whenever they emit energy. Next unit was periodicity, so this is periodic trends, all about the table of elements. First question asks us to give examples of elements that are in the same family and series. So a family is the same thing as a group, same thing as a column. So you can pick any column, and those would all be in the same family, group, column. Those are all the same. A series, on the other hand, is something that goes across a row. It's also called a period. So I just picked this one. These guys are all in the same row. They are the same series, same period. Next question asks us to complete the table about family names. So alkali metals, those are going to be in column 1, the first column. Column 18, all the way over on the right, is of course noble gases. Halogens, those are found in column 17. And column 2 is the alkaline earth metals. So the difference, column 1 is alkaline metals, column 2 is alkaline earth metals. Halogens have very high ionization energy. Explain why. So again, in that last slide, we saw that halogens was everything in column 17. So these guys are all going to be halogens. Ionization energy is the energy needed to knock an electron off of an atom to form an ion. So it's how much energy I need to knock one of those electrons off. Halogens are in column 17, which all have 7 valence electrons. Now, every element on the table of elements is trying to have the same electron configuration as noble gases, which of course have 8 electrons and a full octet. So, every atom is trying to be more like the noble gases. So everything in column 17 with 7 electrons, they're really close to having a full octet. They just need one more. So they hold on to the electrons they have very tightly. They don't want to lose any because that puts them further away from their full octet. Therefore, it is very difficult to knock an electron from a hydrogen because they hold on to them so tightly since they're so close to that perfect configuration. Complete the table about periodic trends. So the first periodic trend is electronegativity. This is a measure of how strongly an atom attracts an electron. So the more electronegative an atom, the more strongly it is going to attract electrons. So as we go across a series, which is again the same thing as a row, same thing as a period, these words are all interchangeable. So as I go from left to right, do we see that the electronegativity is going to increase? This is because as we go across those rows, we get closer and closer to that noble gas electron configuration, closer and closer to that full octet. So we see that these atoms are very attractive to electrons because they just need one more to have that full octet. Atomic size or radius, that's just going to be from the center of the nucleus to the edge of the electron cloud. So we're thinking about how big these atoms actually are. This decreases. So as we go across, we get more and more protons. So that nucleus becomes more and more positive. So we are going to hold on to those electrons just a little bit closer because it's more positive. And that is going to cause the size of the atom to decrease. First, ionization energy. Again, it's just how much energy I need to knock off an electron. First ionization just refers to the first electron. Second ionization would be how much energy would I need to knock off the second electron, etc., etc. So that is going to increase. Again, as I go across the row, I'm getting closer and closer to that perfect octet. So I'm going to hold on to those electrons very tightly. Shielding effect refers to how the outer electrons are blocked from the nucleus by the inner electrons. So as I go across a series, that's actually constant. The reason why, I'm looking at layers of electrons. I'm looking at the energy levels of those electrons. So more layers means more shielding effect. More layers is more energy levels. As I'm going across a row, that's all the same energy level. So adding more electrons to that is not going to increase the shielding effect. It is important to note which of these is the highest for which elements. So the highest electronegativity would be fluorine. The closer something is to fluorine, the more electronegative it is. The biggest radius is francium. So the closer something is to francium, the bigger the radius. Highest first ionization energy is going to be fluorine. So the higher the ionization energy, the closer on the periodic table that element would be to fluorine, and shielding effect is constant. Summarize the properties of metals, metalloids, and nonmetals. So metals are, of course, shiny. They are great conductors of heat electricity. They are malleable, so if I hit it with a hammer, they can bend and not shatter. They are also ductile. That means that I can draw it into a wire. They're usually going to be silvery colored. Exceptions of that would be like gold and copper, and most of them are going to be solids except mercury. Nonmetals are the complete opposite of metals. So those are going to be dull. They do not conduct. They are brittle, which means if I hit them with a hammer, they will shatter. And they're usually many different colors. So, for example, carbon is black, sulfur is yellow, bromine is a reddish liquid. Many of them are also going to be gases. So obviously oxygen, nitrogen, fluorine, these are all non-metals, so they're going to be gases. Metalloids. Those are just something that's in between the two, and these are the most interesting and most useful of these categories. The most known one is going to be silicon, which is of course used for computer chips. It's a semiconductor. So that makes these metalloids useful for all kinds of electronics, computer chips, that sort of thing. Unit 4 is metallic and ionic bonding. So using the information in the data table below, answer the questions that follow. So first thing that I need to do, I need to look at the results of these 4 different tests here and determine which one is ionic, metallic, polar, covalent, or nonpolar covalent. So let's start with the easy one. We know that metals conduct electricity. So the only one that conducts here we see is going to be C. So that's all I need to know to determine if something is metallic. The other one over here, the only thing that has an answer as yes is going to be the nonpolar, like dissolves like. So nonpolar will only dissolve in nonpolar. So the only one that has that is D. So that leaves me with A and B and polar, covalent, and ionic. So if we look at A and B, we see that they're pretty much the same. They do not conduct, they dissolve in polar solvent, and they do not dissolve in nonpolar solvent. So that's all pretty much the same. The difference here comes in the melting point. So for A, we have a high melting point, whereas for B, we have a low melting point. So if you see high, and we see yes, that it dissolves in a polar solvent, that tells me that that is going to be ionic. If we see low and yes, that tells me right away that it will be polar covalent. So these are the key indicators you should look for to answer this question. A polar solvent could be something like water. Nonpolar would be something like oil. So an ionic compound could be something like salt. A polar covalent would be something like sugar. We all know that sugar dissolves in water and that it melts at a low temperature. So you can melt sugar on your stove. You can't melt salt on your stove. You can dissolve it really easily in water, but you can't melt it. C is our metallic, so that could just be like gold or silver or whatever. Pick your favorite. Non-polar covalent, these are a little bit more difficult to think of, common household things, but that would be something like oxygen or oil. Name the following ionic compounds or give the formula. So first we start off with NaCl. So we got to name the pieces here. Na is of course going to be sodium, and Cl is chlorine. So whenever we go to name this, we first write the metal, and then we write the nonmetal, but we're going to change the ending to "ide." So this is going to become chloride instead of chlorine. Next one, we're given a name, and I want the formula. So I have iron 2 carbonate. This one is a transition metal, and I know right away because I've got this 2 here. The Romans are only for transition metals. So of course iron is Fe, and carbonate is CO2. So now that I've identified these, the next thing I need to do is figure out charges. So for iron, iron is a transition metal, so there's no clever way for me to determine the charges here. That's what I need this guy for. So that Roman numeral 2 tells me the charge on iron. It does not tell me how many, it tells me the charge. Carbonate, the charge on carbonate is, of course, -3. So I'm just going to draw these parentheses. So what we do now, we take these charges. This guy needs to come down here, and this guy needs to come over here. The reason we do that, I need the positive and negative charge to equal out to 0. So if I have 3 irons, and each of them has a +2 charge, that gives me +6. If I have 2 carbonates, and each of them is -3, that would give me a charge of -6. So -6 and +6 together would give me 0. So what I would write in the end is Fe3 CO2 2. That just tells me there's 2 carbonates. Name the following ionic compounds or give the formula. This one is PbNO3 4. So once again, let's start with naming these guys. So Pb is lead, and NO3 is nitrate. So lead is a transition metal. That means that I need to indicate the charge with Roman numerals. The problem here is that I'm not given the charge. So how do I figure that out? That's where we're going to take a look at the nitrate. So I know that nitrate, NO3, that has a charge of -1. There are 4 of them, so that means my total negative charge is -4. For lead, in order to balance out this -4, I need to have a +4, because +4 and -4 together will give me 0. So lead must have a charge of +4. So this would be lead 4 nitrate. So I just checked the other thing, the thing that wasn't lead, to figure out what the charge was for lead. So here's a general procedure for naming an ionic compound. Again, we got to worry about those 2 pieces, the metal and the nonmetal. Got to worry about the charges, watch out for polyatomic ions, watch out for transition metals, and crisscross the charges. So determine the metal, so either the name or the symbol, and determine the charge on the metal. 2 ways to do that. Check for Romans, that would just tell you what the charge is, or use the table of elements for non-transition metals. If you are given a formula, you're trying to figure out the charge, so that's what we did for the lead 4 nitrate. We looked at the anion, we looked at the thing that wasn't the metal, and kind of worked backwards to determine the charge that the metal must have. Determine the charge of the nonmetal. So watch out for polyatomic ions, and you can use parentheses to kind of keep those together. Those have one overall charge. Most of them are negative. And then use the table of elements for, if you have an element, just to figure out the charge. And if it is a pure element, change the ending to "ide." So something like oxygen would become oxide. Nitrogen would become nitride, etc., etc. Crisscross the charges if you're writing a formula. So cross those charges out. Remember, we want positives to equal negatives. And then put the metal and nonmetal together for the name. Use those Romans to indicate the charge, and watch out for polyatomic ions. A good indicator of polyatomic ions, if it ends with ite, I-T-E, or if it ends with ate, it's probably a polyatomic ion. You should check that sheet. Next question is to complete the sentence. So this is important because a metal and a nonmetal is a good way to identify an ionic compound. So the trick to naming these is to be able to identify the compound type. So a metal and a nonmetal makes an ionic compound. Typically, the metal loses electrons, forming cations or positive ions. Conversely, the nonmetal will gain the electrons that the metal lost, and that will form a negative ion, also called an anion. Next question asks us to color code, and this is important because this is how we recognize if something is a ionic compound. So I'm looking for metals and nonmetals. So my nonmetals, I'm going to make those green. So all of my nonmetals are going to be on the right side. So these are all nonmetals. And over here, the one exception is hydrogen, hanging out by itself. So these are all going to be my nonmetals. The metalloids are most of the ones that touch this staircase here. So boron, silicon, these guys right here, germanium. All of these guys are going to be my metalloids. Key exceptions here are aluminum, which we know to be a metal, and polonium. So that's also a metal. So that means that everything else on here, most of the table of elements, is going to be metals. So all of these guys are our metals. And don't forget the lanthosides and anthrosides down here. Next question asks us how we can explain the properties of metal, such as malleability and conductivity. So that's going to be the electron C model. In the electron C model, the metals give up electrons, forming metal cations. So these +3s on these purple guys, those are going to be all some metal that gives up 3 electrons. So those are all +3. Those 3 electrons are now flowing between the metal cations. This gives us our conductivity. These electrons are able to carry heat and electricity with them, making them good conductors. And they also, since they're flowing between these positive ions, these cations, it insulates them from each other. So if I hit them with a hammer, instead of the positive charges repelling and causing it to shatter, those electrons are kind of like grease that allows them to slide past each other so they don't shatter. What type of substance does not conduct electricity as a solid, but it does conduct once added to water? So these are going to be ionic compounds. An example of an ionic compound would be something like salt, NaCl. That's like the poster boy for ionic compounds. And salt does not conduct electricity as a solid. So if I take a conductivity meter and stick it into some solid salt, no lights. But if I drop it in some water, it does. So as a solid, the ions in sodium chloride are trapped. They can't move, so they can't conduct. But once you drop it in water, the ions are able to move. They dissolve and break apart. So it's able to conduct. Pure water does not conduct electricity, but it's very rare for us to come across pure water because it is such a good solvent. It's very good at dissolving things. Unit 5 was about covalent bonding. So first question asks us to draw some Lewis structures. So we're going to start off with an ionic bond. Ionic bonds are always going to be single bonds, which is of course 2 electrons. So here I have potassium. And if you look on the table of elements, potassium is in the first column, which means that we've got 1 valence electron. Fluorine, on the other hand, is in column 17, one of my halogens. So this has 7 valence electrons. Everything in column 17 has 7 valence electrons. So we do top right, bottom left, top right, bottom. That gives me my 7. And we can kind of see here that there's a hole that will be filled in with that 1 electron. So whenever we go to draw this, it's okay to kind of move the dots around. As long as the ones that are paired up stay paired up. So we got fill these guys in. So this right here is a single bond. Potassium, this is an ionic compound, so potassium is giving away an electron, making its charge +1. Fluorine gained an electron, making its charge -1. Next one gives us an actual covalent bond. So this is a single bond. So for fluorine, again, we already figured out that that's 7 valence electrons. This is F2, so I've got 2 fluorines. So you can kind of see that there's a hole that we can fill in here. So the way we'll draw this, that's my single bond. So we're talking about 2 electrons there. Fluorine has a total of 7. I've accounted for 1, so those other 6 that are left over, those need to go around here. And again, we can kind of shift these around. Just make sure that they are paired up. If they're paired up over here, whenever you first drew them, they should be paired up whenever you draw them for the Lewis structure. Next question is double covalent bonding. So, of course, the double bond is going to be a total of 4 electrons. So, I've got a couple choices here. I've got carbon. Carbon has 4 valence electrons. And oxygen. There's 2 of those. Has 6 valence electrons. So you can kind of see, whoop, drew one too many. You can kind of see that there's a couple of holes here where the carbon electrons could fill in. So one can go there, another one can go there. These guys can come down here. So we can kind of see that we're going to fill in these electrons. So the question is, which one of these is going to be in the middle? It's going to be the one with the least number of valence electrons, but never hydrogen. We don't have hydrogen here, so we don't need to worry about it. So the one with the least valence electrons is carbon. So carbon is in the middle, and there's 2 oxygens. We are dealing with double bonds here. So I'm going to draw my 2 double bonds. And each of these double bonds is 4 electrons. So half of them come from carbon, so I'll draw those in. And then half of them must come from from oxygen, so I'll draw those in as well. So there's carbon with its 1, 2, 3, 4 electrons taken care of. And then we have oxygen, which is supposed to have 6. Now I've only accounted for 2 out of the 6, so these other 4 need to go over here around the oxygen. Last example shows us triple covalent bonding. So that would be like what we would find in nitrogen. Nitrogen is in column number 15, which means it's got 5 valence electrons. So 1, 2, 3, 4, 5, and this is N2, so I'm just going to draw both nitrogens. So we can kind of see that there's a bunch of holes here. I'm missing here, missing here, missing here. So they're going to kind of share those electrons in order to get their full octet. So I've got 2 nitrogens. They're connected by a triple bond, which means 6 electrons. So let's draw the bond. Now let's draw our electrons. So if there's 6 electrons, half of them must come from one nitrogen, and the other half must come from the other. So there they are. I've accounted for 3 of nitrogen's 5. I see that I've got these guys paired up over here, so these guys will go together. Same thing on the other side. Next question is some simple naming. Covalent compounds are easy to name. You just got to remember the prefixes. Never start with mono and change the ending to "-ide". So I've got, first one, I've got CS2. So C is, of course, carbon. There's only 1 of them, but I never start with mono. And then I have sulfur, which becomes sulfide. And there's 2 of them, so it's carbon disulfide. Dinitrogen pentoxide. Nitrogen is N, oxide is O. Dinitrogen is 2, pentoxide is 5. NO2. Again, we have nitrogen. There's only 1 of them, but I never start with mono. I have oxygen, but that becomes oxide. And there's 2 of them, so this is nitrogen dioxide. Compare the behavior of electrons in polar and nonpolar covalent bonds. So covalent just means that electrons are shared. If we are polar, that means that we are sharing equally. If we are polar, we are sharing unequally. An atom is going to hog the electrons. Nonpolar is where we would share equally. So the electrons spend the same amount of time with each atom. So here I got a polar and nonpolar set of atoms. The first one, this is going to be nonpolar. So the electrons are spending equal time with each atom. Whereas with this polar one, we see that the electrons are going to spend most of their time around the more electronegative chlorine. A quick test for polar and nonpolar, if you can cut it in half, and it's the same on both sides, it's going to be nonpolar. If you can cut it in half, and it's not the same, that's polar. Indicate the bond type for the following Lewis structures. So again, if I cut it in half this way, not the same on both sides, so that's polar. If I cut this in half, no matter how I do it, nonpolar, it's the same. This guy right here, polar. This one right here is kind of a trick, because we want to say, because it's different on 2 sides, we want to say that it's polar. But we need to be careful, because we have a metal and a nonmetal. So that tells me that this is ionic. The other big symbol here, the other big key is that we've got the charge. So that tells me that's ionic. These guys, all of the other ones, these are two nonmetals, which is, of course, covalent. What intermolecular force explains the unique properties of water, such as the high boiling point and the fact that it's a liquid? This is due to hydrogen bonding. Determine if the following are polar, nonpolar, or ionic. So there's a couple different ways we can do this. I like just to look at the shape. So I2 is just going to be an I connected to an I, HCl, CO, and NaF. So if I divide this in half, it's the same on both sides, so it's nonpolar. This guy is different on both sides, so it's polar. Same thing here, polar. This is again a tricky one because I've got a metal and a non-metal. So we want to say that this is polar because it's different on both sides, but it's actually ionic because we have a metal and a non-metal. These guys here are all non-metals. So they are covalent. In order to be polar or nonpolar, you gotta be covalent. Determine the molecular shape for the following. So this is where you're going to need to use that VSEPR sheet, and you can kind of look on that and kind of compare. This is CH4. Carbon has 4 valence electrons. It's never going to be hydrogen in the middle. So this looks like this. And if we were to put this into 3 dimensions, this would be tetrahedral. Okay, HCl, I've only got 2 atoms, right? The only way to connect 2 points is with a line, so this is linear. So anytime you have 2 atoms, doesn't matter what they are, NaCl, hydrogen, oxygen, any of the diatomics, those are all going to be linear because there's only 2 atoms. For water and for this compound here, oxygen and sulfur are pretty much the same. They have 6 valence electrons, so chemically speaking, they're interchangeable. So if I have oxygen or sulfur, okay, they're all going to have the same number of valence electrons, and that's 6. So the hydrogens will come in here where there's a hole. Hydrogen each has 1. So we see right away, no matter how I cut if I cut these in half, they're different on both sides, making them polar. And the shape here, these are both going to be bent. So anything with the formula of, like, you know, something like that is probably going to be bent. Last unit here is chemical reactions. First question asks us to make an activity series for metals A, B, C, and D. So what I recommend you do to avoid confusion, every time that you see reaction, you can count that. So we see that for D, we've got 3 reactions, 0 for C, 2 for B, and 1 for A. So the most reactive is going to be the one with the most reactions. So the one that is most reactive with 3 reactions is D. Next up comes B. Then we've got A and C. So this has the most reactions. This has the least. So that means that D can react with everything except for a compound containing itself. So that's going to be the most reactive. C does not react with anything, so it's the least reactive. Which metals will replace B? So the only way that B can be replaced is with something that is more reactive than it. Okay? So we know that the only thing more reactive than B, again, here's our series. The only thing more reactive than B is D. So this would be BCl2 reacts with D. D is more reactive, so it kicks out B to make DCl2, and there's B by itself. Determine the number of oxygen atoms present for these different molecules here. So what this is telling me is that I've got 2 aluminums. This 3 applies to everything inside, so this is saying that there are 3 of these guys. So of course I've got 21. This is telling me there's 2 B's. And this 3 applies to everything inside, so there's 3 of these guys. And those add up to make 9. Next page is balancing, and there are, of course, some naming here. So we've got calcium nitrate. Calcium is Ca. Nitrate is going to be NO3. Got to check my charges here. Nitrate has a charge of -1. Calcium has a charge of +2, so we get CaNO3, 2. Reacting with aluminum sulfate. So these charges crisscross. If you can't get these charges right, you're not going to be able to write the formula correctly. So you need to be able to check your charges. We make calcium sulfate. Whenever we crisscross these 2's, we just get 2 and 2, which is the same thing as 1 and 1. And then we get the aluminum nitrate. So these guys are going to crisscross. All right, so now that we've done this, we can draw our boxes. So the reason we draw these boxes is to remind us that I can't change anything inside here. The only numbers I can change are the big numbers in front. So now we can take our inventory. So I start with Ca. Nitrate appears on both sides, so I'm just going to keep it together. And same thing for sulfate. So on this side, 1, 2, 2, and 3. So this 2 means I've got 2 of these guys, 2 and 3. On the other side, I've got 1, 1, 1, and 3. So let's start off with something that is like a 2 and a 1, or a 3 and a 1, because that's easy. So if I put a 2 in front of here, that becomes 2, but this becomes 6. Okay, let's deal with this. So if I put a 3, that becomes 3, but this becomes 6. So now let's fix the other side. So I've got 3 calcium and 1 calcium. So if I put a 3 here, okay, that becomes 3 calcium. 3 times 2 gives me 6. Next one's a little easier because it's already written for us. So all we got to do is balance it. So we draw our boxes first. Again, I don't want to change anything in the boxes, so I can't change the little subscripts. Now let's take our inventory. We've got hydrogen and we've got chlorine. So this is real easy. Stick a 2 there. These both become 2. Next one is again written out for us. So we draw our boxes. Can't change anything in there. And now we need to take our inventory. So we've got sodium, calcium, and we've got nitrate. Again, nitrate appears on both sides, so I'm just going to keep it all together. So let's take care of the nitrate, put a 2 here. That becomes 2, but uh-oh, that's 2 as well. So I need to come to the other side. There we go, balanced. Metallic tin reacts with oxygen to form tin 2 oxide. So tin is SN. We're not going to worry about charge because it's by itself. Oxygen, remember, is one of our diatomics. So it's going to be O2, not just O. And we're going to form tin 2 oxide. So tin plus 2, and the Roman numeral tells me the charge. Oxygen is minus 2, so we crisscross and we just get SNO. Alright, now we need to balance, so let's box off. Can't change anything in the boxes. And now we take our inventory. So I've just got tin and oxygen. So put a 2 here, and then put a 2 here, and there we go. Next one, ethane burns, so this should be pretty easy. It says that it burns, so right away I know that this must be a combustion reaction. So ethane is C2H4. It is burning, so that means it's reacting with O2. And we always make CO2 and H2O. These are always the products. So now we're ready to balance. Boxes first. Now we need to take our inventory. So I've got carbon, hydrogen, and oxygen. Please be mindful. We've got 2 oxygens here and 1 here, so I need to be careful. So let's take care of carbon. Put a 2 here, that becomes 2. 2 times 2 gives me 4, plus 1 more gives me 5. Okay, take care of hydrogen. So that becomes 2 oxygens from water, 4 from carbon dioxide, so that gives me 6. So if I just put a 3 in front of this, that gives me 6. Next question, circle the reactants. So everything before the arrow is going to be reactants, so those guys. As far as reaction types, this one I've got 2 things switching places, so this is double displacement. This guy right here, let's switch to something else. This would be double displacement. This guy right here would be decomposition. One thing is being broken down. This is single displacement. This guy right here is 2 things coming together to make one, so that's synthesis. And this last one here is oxygen, so that's combustion. Which of the following would be a precipitate? So precipitate is just another word that means solid. So NaCl is always soluble. So that will always be aqueous. AgNO3. Nitrates are always soluble no matter what. So this would be aqueous. Sodium, again, we have sodium and nitrate here, so that's going to be aqueous. So if we look down here, halides are always soluble unless I have silver. So that's going to be my solid or my precipitate. Silver chloride. Silver's tricky. Remember, it's hiding out with the transition metals, but it actually has a charge of +1 always, so it's not really a transition metal. Give the coefficients and the subscripts. So the coefficients, those are the numbers in front. So for this one, the coefficient is 1. Remember, there's like an imaginary 1 there. The subscripts, there's 2 of them. We got 3 and 2. Coefficient for this one is the big number in front, so that's 4. The subscripts are the small numbers, so that's 3 and 4. What is always conserved during every chemical reaction? So, the law of conservation of mass says that the mass before and after any chemical or physical change remains constant in the universe. So, mass is the same thing as matter, which is the same thing as energy. So all of these things are conserved or kept constant.